because it's 2 mass numbers up but 4 neutrons across. You see this trend a lot. That's the third one. I was going to keep that for a secret, so if anybody's falling asleep now, pay attention to that. Everything else was an alpha particle up. 2 protons, 2 neutrons would have put us there, but this is a double skip. This is a single skip, though. Vanadium 51 to manganese 55, alpha particle up. Manganese to cobalt 59, same thing. They're all on there. From cobalt, the copper ends up splitting like the chlorine did before. So if we move this down here, you're going to see chlorine split exactly like the copper does. And that's on the screen, but it's not on your screen. It's showing half of it here. Move. So again, these same abundances you'll see. 34's even, has a copper and a zinc above it, stable copper, zinc above it. So when you look at the big picture of this, you go through, these are all messed up. See, I know the tape's running out, so I feel like I'm wasting my time. What, I've been wasting your time too? We'll zoom out even more to show, because this is reaching the end here. As you look at the chart, you see the trends coming across. 2 ups across are stable, then all of a sudden an up. Across, there's lots of isotopes there. Good little trivia question is, what element has the most isotopes? It's a good little exercise. Teachers, if you're looking for something to give the students to do, search the chart of the nuclides and find which element has the most naturally occurring isotopes. I'll tell you, it's tin. But here, when we look at this table, we notice there's a lot of krypton isotopes. Krypton's a noble gas also. So chemically, krypton is stable, but nuclearly, krypton is stable. Again, we see here these trends going up and down. Okay, there's no elements in between there. And these are even and odd number combinations coming in there. So something different comes into play. It's almost like the 40 neutrons gives it more stability than the 34, 35, 36 protons in there. And then again, when you come across, you'll see that arsenic, As, 100% of the isotopes that you find are 33 protons, 42 neutrons. Exactly an alpha particle up from that. Bromine does the split just like chlorine. Those two are in the same table of the elements column, okay? This is a trend I start seeing. So there's other splits up here. If I could just have the hand and the magnifying glass, this would work perfect. Magic number comes up through yttrium here. For some reason 50 is a magic number. 50 neutrons gives us a lot of ones stable there. Molybdenum has a lot of isotopes. See that? The most abundant is going to be the biggest. Technetium, which kind of is just one of those ones they make questions out of. RH, 100% isotope. Up from that, silver splits. 2 isotopes of silver. Now silver has a +1 oxidation state. Above silver was copper. Copper had the split like the original chlorine. And notice again that here our stability is going up and down with 60 neutrons, 62 neutrons. Nothing in between there. Cadmium has a lot of isotopes. The biggest one being right in the middle there, 64 or 66 neutrons. And again, when you go up, see the way there's these trends here. As I was saying, the element with the most isotopes, tin, is considered to have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did it right. So when you look, you'll see the most abundant tin has the same number of neutrons as the stibnium, which does a split. There's only 2 isotopes of the element above tin that has the most isotopes, 10 of them. The next element up only has 2. Well, look at down below here. Indium, the element below tin, that did the split also. Almost even to even, probably twice as much of the 115 isotope as there is of the 113. But up here, odd numbers again, 121, 123. These 2 isotopes are roughly 50-50. I find this fascinating. Now, if you look at the elements across here also, if you could look at the whole chart in one piece, we see a lot of xenon, the next noble gas above krypton. Lots of isotopes, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's a good trivia question. What element next to tin has the most isotopes found in nature? Well, it's a noble gas, and it's xenon. Now barium, see, barium has these 5 right in a row, almost even in abundances. 82, 81, 80, 79, it doesn't matter the odd even number of the neutrons. At that thing, for some reason, with 56 protons, it's stable. But now, we'll use our hand here, this thing's almost doing a big giant ladder effect. You see this? So I want you to go and look for yourself and just find interesting little trends here. All the way across the bottom, all the way up, all the way across, roughly, but there's a lot of isotopes in there. 1 isotope of that, again, coming through here, a couple of these are radioactive. Naturally occurring radioactive. I hear a lot of people that like to look at the periodic table here. I'll show you real quick. Oh, those elements they're all radioactive. They only last a few seconds, okay? Anything above uranium, we're going to see the reaction where neptunium and plutonium were made by Glenn Seaborg and Al Giorso and Darlene Hoffman and Macmillan and Greg Copeland and all those guys out there. I know I forgot a bunch. So these elements, americium, is actually in fire alarms, continuously spitting out an alpha particle, I believe. So you can get enough of it together that it'll last 30 years in a smoke detector. What it does is it blows straight across clean air, and alpha particles hitting a detector, everything's fine. But when smoke gets up there and starts absorbing the alpha particles, the detector isn't getting the alpha hitting it to make it not ring. So then it rings. Point is, americium is one of those elements that they make in the lab because it doesn't occur in nature. But when you make americium, it decays fast, but you can get enough of it together. So all these other elements here too. The one I like, they said the most expensive element in the world, I think, was californium, because they actually make enough of it to sell it and make bigger elements out of it. So I believe they make that in Tennessee at the Oak Ridge Laboratories. So this is kind of neat that the greens just were skipping through there. Where was it? Real green. The elements kind of did. So germanium was named for Germany. Can you see Frankfurt in there? Silicon Valley. Indium. All the colors of indigo coming out. Rhodium, that's Latin for rose. Ruthenium, that's Latin for Russia. Russia's already in there, and then they went and they named this one down here dubnium. Well, Glenn Seaborg here, element 106, told me personally that we are sticking with honium for 105. Now they call it